All right, now for the third set of 4 of the Chapter 9 lecture slides. We're still talking about stress transformation, and now we're going to introduce Mohr's circle. So in this section, we're going to see how to apply those equations that we've derived from our previous sections in Chapter 9 for plane stress transformation using a graphical solution. That's going to be more convenient, easier to use, and I think a lot easier to just remember. It's also going to just allow us to visualize how the normal and shear stress components vary as the plane on which they act changes its direction as it rotates about that z-axis, or whatever that third axis is. So if we think back to what those stress transformation equations were, if we do a little rewriting, add some stuff together, we can eliminate that parameter theta from the equations. And for any specific problem where we know or are given sigma x, sigma y, and tau xy, we can arrange those equations into this equation, where we have our transform sigma x minus our sigma average quantity squared, plus tau x prime y prime squared equals a radius squared. So this equation is that of a circle, as you hopefully learned at some point in your math studies through the years. Okay, our sigma average, again, is this sigma x plus sigma y over 2, just the average of our two normal stresses on our original element. And then the radius was the radical that was underneath our sigma 1 and sigma 2 principal stress equation, and then also the equation for our max in-plane shear stress. If you want to take a closer look at the full derivation, it's not too important. That's on page 469 of the Hibbler textbook. Okay, so if we establish coordinate axes where our x-axis is our normal stress, sigma, and that's going to be positive to the right, as usual. But to keep our sign convention straight, as we'll see, we need shear stress to be positive going down. So that's an important detail for plotting these stresses. We have normal stress positive to the right, shear stress positive downward. And if we plot that previous equation, we get a circle. That circle has the radius r that I mentioned, what was under that radical, and the center of the circle is always going to be on our sigma axis, located at this point we'll call C, with coordinates of sigma average on the sigma axis, and then, of course, 0 on the tau axis if it has to be centered on the sigma axis. This circle that we just drew is called Mohr's circle, and it's called that because it was developed by this old dead German engineer named Otto Mohr. And the next few slides you should use as your reference for how to draw the circle and how to use it in an efficient manner. So basically what Mohr's circle is showing us, though, is the coordinates for your normal stress and shear stress at any point as you rotate your element. The next slide will show us how to actually draw it, but we'll just talk a little bit about what the different points actually mean. So for instance, when we're given an element with our original sigma x, sigma y, and tau xy, we can plot that as point A in our sigma tau plane. So at this point, we're at sigma equals sigma x, and tau equals positive tau xy, because it was up here on the right. That's our point A, and we'll use that as a reference point. And so then when our x-axis and our x-prime axis are coincident, meaning they're overlapping each other, that's when theta is equal to 0 degrees. If we rotate around the circle here, that's going to be a 2 theta rotation. So a 2 theta rotation of 180 degrees is going to correspond to a rotation of 90 degrees on our actual element. So if we're going from sigma x rotating 90 degrees, that takes us to sigma y. That is going to correspond to this point G, which is going to be located at sigma y and now negative tau xy. So they're on opposite ends of the circle. So our two axes are connected by a diameter on our circle. That's mentioned here in slightly different words. If we consider rotating the x prime axis 90 degrees counterclockwise, as in B here, then sigma x prime equals sigma y, and tau x prime y prime equals negative tau x y. Okay, that's point G. Again, repeating what I said before, a rotation theta on our element is going to correspond to a rotation of 2 theta on our circle. And that's going to be in the same direction, counterclockwise, counterclockwise here. That's thanks to our established sign convention, though that's not obvious in this case, but is in any other rotation that's less than 180 degrees. So, once your Mohr circle is constructed, you can use it to easily determine your principal stresses and the max in-plane shear stress and the angles at which they occur, or the stress on any arbitrary plane. So you can do anything with the circle. All you need to do is follow these steps. First of which, you need to establish your coordinate system. Again, horizontal axis is sigma, positive to the right. Vertical axis is tau, our shear stress, positive downward. After that, you need to use your positive sign convention for your original stress element. And then plot the center of your circle at sigma average, comma 0, and then your reference point at sigma x, comma tau xy. Okay, so in order to draw a circle, you need 2 things. You need to know the center of it, and then you need to know a point on the circle. Once you know those things, you can find your radius, which is what you need to find all your important maximum values shown here. And you can sketch your circle around by putting a compass on the middle point, your pencil on the outer point, and sketching your circle. Okay, you can find that distance between the center and the reference point. That's again the radius of your circle. And then sketch the circle. Now your principal stresses are just going to be located at these points B and D, where B is sigma 1 because that's your larger normal stress, the one that's further along your sigma axis, and D is going to be sigma 2, okay, because that's your minimum normal stress. Sigma 1 is always greater than or equal to sigma 2. Okay, so again, those principal stresses are where tau is equal to 0. That's shown here again for you on the element. And in order to find the angles on which those principal stresses act, you can just use trig functions to find the angle 2 theta p1 here. And once you know that 2 theta p1, you can just add or subtract 90 degrees from what theta p1 is. Because remember, if we're going from our sigma 1 to our sigma 2, we just have to add 90 degrees or subtract 90 degrees. So from this reference line AC, 2 theta p1 is found by, I usually use inverse tangent of the tau xy divided by this horizontal distance here, not the whole distance, right? You need to draw your right triangle there and do inverse tangent. And then make sure that you divide by 2 at the end because this is 2 theta p1. Right? And then this is showing you the max in-plane shear stress. It's just going to be the radius. Right? You find this radius by just using the Pythagorean theorem. Find that height here. That's going to be tau xy. And then this base here, you can just find using a little bit of arithmetic. Square root of the sum of the squares will give you your radius. Right? So your max in-plane shear stress and the corresponding normal stress components are going to be from these points E and F. Right? Remember, C is at our sigma average. And we talked about that a bit in worksheet number 2 and in the second part of the chapter 9 lecture slides, that your normal stress is sigma average, meaning sigma x plus sigma y over 2 on each face when you have max in-plane shear stress. So again, the max in-plane shear stress is just your radius. That's point E. And then the negative max in-plane shear stress would be point F. So again, we don't really need to calculate it twice because it's going to be the same value. They're just going to be going in opposite directions according to our sign convention and according to our shear equilibrium on our element. If it's going up in the y direction here, it needs to be going in the positive x direction on this face here. and then make sure that the points meet at opposite corners so that you're in rotational equilibrium. Okay, and remember that same thing for 2 theta S1. If we're rotating 2 theta S1, that corresponds to theta S1 on our actual element. Okay, Mohr circle is just a visualization, a representation of what's happening, but we are using 2 theta instead of theta to get it to be a circle. And I mentioned before, you can find your normal and shear stress components on any arbitrary plane or x prime axis defined by an angle theta just by using some trigonometry, doing a little bit of math. But normally I'll just use equations when finding these. And we usually just have you use Mohr circle to visualize your principal stresses and max in-plane shear stress. And when we start doing 3D Mohr circle in the next section, to compare all 3 of our principal stresses and all 3 of our potential in-plane max shear stresses and our absolute max shear stress. All right, so now we have some examples to show you how to use Mohr circle to find the principal stresses pretty quickly. And I'm going to put these on a separate video, so I'll see you over there.